Here is a review question on Fourier series. We're given a function that is this absolute value type function, and outside of the interval minus pi to pi, the function is periodic with period 2 pi. Now we're asked to do a few things. We're asked to sketch this f, calculate the Fourier series, and then we're asked to do a few things with that Fourier series to form other interesting results. Now, just to refresh our memory, a Fourier series is just a series involving lines. And to calculate a Fourier series from a given function, you want to calculate these coefficients, the a naughts, the a sub n's, and the b sub n's. And to do that, you use integration. Now, if you look at these intervals of integration, it is a symmetric interval, minus L to L, where L is some number, half the period. When f is a special form, an odd function or even function, a lot of these calculations simplify. All right, let's have a look and work through this step by step. Make a sketch of f on this interval. So what I like to do is just sketch this function on the interval, say, minus pi to pi, and then use the periodicity. So you sketch the function and then you copy what you've got, move it and paste. Copy, move and paste. Okay, so let's say this is the interval of interest. This is our absolute value type function. What we would do is take that graph, we would copy it, move it to the right, and paste. Copy it, move to the left, and paste. Okay, so all right, so we get something like a sawtooth wave. Now, this, if you look at the graph of f, it is clearly an even function. It is clearly an even function. Because you can see we have this reflection in the vertical axis. Okay? So just to refresh your memory, we talk about even function. This is the sort of algebraic definition, but you know, if you have a reflection in the vertical axis, then you have an even function. Well, you know, x squared is an even function. The cosine function is an even function. And you can contrast that with an odd function. An odd function, well, you can tell whether you have an odd function or not. Take the graph, rotate it 180 degrees. Do you get the same graph that you started with? If you do, then it's an odd function. So y equals x, that's an odd function. The sine function, that's also an odd function. So here we have an even function. Now, in part 2, we are asked to calculate the Fourier series for f. And to do that, what we do is calculate these Fourier coefficients through integration. Now, like I said before, sometimes these things will simplify when we have odd or even integrands. Well, this is an important lemma. If we have an even function, then we do get some simplification. The b sub n's in our formula are all 0, and we can calculate the a sub naught and the a sub n just by, instead of integrating from minus L to L, you integrate from 0 to L, and you multiply both of these formulae by 2. Okay? So we've got an even function. Let's go ahead and use that, and we can simplify. Okay, since f is even, the b sub n's are all 0. Now the a sub naught and the a sub n's, well, we can calculate them from the previous lemma. Now, remember here the big L is half the period. In our particular example, the period is 2 pi. So L, big L in this case, would just be pi. Now, on this interval, 0 to pi, f of x is just the x function. Now, I've written down, a few things there. You don't necessarily need to write all these things down. All you really need to do is just look at the area under the curve from 0 to pi, and then just divide by pi. Or if you just, you can just do the integration. Okay, so the area of that little triangle is going to be pi squared on 2. Divide by pi, you get pi on 2. Okay, that's easy. The slightly more involved case is with this. Okay, so the a sub n's is given by this, with big L equals pi. Okay, so if we sub in big L equals pi, and note that from 0 to pi, f of x is just the x function, then we'll get the following. Okay, so we're faced with an integration. Let's integrate by parts. Let's choose u to be x and choose v prime or v dash to be cosine nx. So if we want to use our integration by parts formulae, it'll be something like this. U prime or u dash would just be the derivative of x, which is just 1. And v is the integral of cosine nx. Well, cosine's going to go to sine. And then to touch up, I just want to divide by n. So it'll be 1 on n times sine nx. So let's use our integration by parts formula and knock over this integral. Okay, so the integration by parts is u times v minus the integral of the product of the two things you just thought up or just calculated. Okay, so the product of this is just going to be what we have here. Okay, so in the sort of first substitution, I'm going to get sine, something involving sine n pi, where n's a positive integer. So what's sine n pi? Sine pi, sine 2 pi, sine 3 pi. It's always 0, right? If I sub in x equals 0, well, I'm going to get 0 as well. So this whole thing is just going to contribute exactly 0. Now, let's do this integral. Sine's going to go to a minus cosine. And again, I just need to divide by another factor of n. So I'll get something like this. right, so if I sub in x equals pi, I'll get cos n pi. If I sub in x equals 0, I'll get cos 0, which is 1. So if I just sort of rearrange this a little bit, I can take the n squared to the front. I'll get something like this. This is an n squared here, pi n squared. Okay, well, we're slowly forming our representation for the a sub n, the cosine coefficients. Well, what's cos n pi? Well, it sort of alternates in sign, right? Between positive 1 and negative 1. Okay, so I can actually write this in the following way. Okay. Now we've simplified cos n pi. We can keep looking at this and then go, okay, well, when n's even, this is going to simplify a little bit. What's in here will go to 0. When n's odd, I'll get a minus 1 and a minus 1, well, minus 2. So let's just go one step further and simplify a bit more. So this is going to be minus 2. So if I multiply through, I'll get the following. Okay, so now we're at a good spot. Let's just recap what we've calculated. Firstly, because our function f was even, we've got the b sub n's all 0, so no calculations necessary. We also calculated a sub naught to be pi on 2. And the a sub n's, well, depends whether n's odd or even. If n's even, all the a sub n's are 0. And if n's odd, all the a sub n's are minus 4 on pi n squared. So now we've got our coefficients, let's write down our Fourier series, which in this case, because all the b sub n's are 0, will just be a Fourier cosine series, a cosine series. All right, so I like using s f of x as the, I guess, how to denote the Fourier series of a function, f of x. So in this case, it's the following. Now, again, it will be cos n pi x on L. L equals pi, so it'll just be cos n x. All right, so let's just substitute in. Our a sub naught was pi on 2. And I guess I'm going to use, I'm going to use this form straight away for the a sub n's, this sort of less simplified form. Now I can take that 2 on pi out the front because it's constant. Now, what I can do here is actually simplify like I was doing on the previous page and just sum over the odd terms, because this is always 0 if n equals even, if n's even, right? So let's just sum that over the odd terms. I can replace this with minus 2 on n squared. So let me show you. So now I'm just summing over the odd values of n. So when n's odd, remember, this will be minus 2. Okay? Now, if I wanted to simplify that even more, let's go to a new sort of dummy variable. And instead of worrying about the odd terms, let's just go with k equals 1, 2, 3, 4. To do that, what I would do is replace n in the sum and with something that's always odd, say 2k minus 1. and start the sum at k equals 1. Okay, so let's pull this out. What I'm going to do is replace n in here with something that's always odd. And that would be my final form of solution. And we would expect you to come up with a form like that. Okay? Now we can use that form in the following questions. Part 3, 4 and 5 essentially ask you to do something with what you just calculated in part 2. Okay? Let's have a look at that. X be this function here, which is also periodic, the same period as our f, but slightly different, differently defined. By differentiating your Fourier series in part 2, or otherwise, obtain the Fourier series for this new function g. Okay? Well, we're kind of given a hint, we're asked to differentiate. So assuming we can differentiate our Fourier series term by term, let's just differentiate. Now, if I differentiate this function, note that I get this, just ignoring the point x equals 0. If I differentiate this function, I get this function. Okay? So what I'm actually going to do here is take my Fourier series, differentiate it term by term. This will become that. So essentially what I've got is a new Fourier series just by differentiation. Okay? So this is now part 3. So I'm just going to ignore the point x equals 0 because the absolute value function isn't differentiable there, but that's not a big deal. So the derivative of our function f is just our new function g. All right. Well, assuming we can differentiate here, let's differentiate and form the Fourier series for little g. So the Fourier series of g is just the derivative of the Fourier series for f. So let's go up here and differentiate term by term. Well, that's going to become 0, and each term in the series, well, the cosine is going to go to a minus sign. The 2k minus 1 is going to come out the front. So let's see if we can clean that up a bit. Well, the cosine is going to go to negative sign. The 2k minus 1 is going to come out the front, and it'll sort of cancel off with some of these, with one of the factors down here. Okay? So now, just through one differentiation, we've produced the Fourier series, the Fourier sine series, for the function g. How good's that? Okay, so this then is the Fourier sine series for this function. Pretty good, huh? Pretty good. So in many cases, you can take existing Fourier series and work with them, manipulate them to form new series for other functions without going through all the calculations, which is great. All right, part 4. What does the Fourier series of g, this function here, converge to at x equals pi? Okay, well, let's draw a little function, a graph of the function of g. G is essentially like a square wave function. Okay? Again, it's periodic, so let's just draw in this part on this interval and then copy and paste. Okay. Now, the question asks us, what value does the Fourier series of g converge to at x equals pi? Well, this function, g, and indeed the original function f as well, is piecewise continuous and has a piecewise continuous derivative. That means it satisfies the conditions of Fourier's theorem. Fourier's theorem says that, well, the last part anyway, if f's continuous at a point, then the value of the Fourier series and the original function are the same. Whereas if f has a jump discontinuity at the point of interest, the value of the Fourier series is the average of these two limits. So this is the right-hand limit as we approach c from the right. This is the left-hand limit as we approach c from the left. So let's talk about the point pi. That's our point of interest. G has a jump discontinuity at that point. So Fourier's theorem says, let's look at the left and the right-hand limits of g, average them, and that's what the value of the Fourier series must be at pi. So the right-hand limit, what's the graph approaching as we come in from the right? It's approaching -1. The left-hand limit, we're approaching +1. So you average those two things, you get 0. Essentially, it's just the average of the jump. So by Fourier's theorem, the value at this jump discontinuity point is just the average of these two limits. From the right, it's -1. From the left, it's 1, 0. So essentially, the value of the Fourier series is just 0 at x equals pi. Now, our last part for this question, use the Fourier series for g to obtain a series representation for pi on 4. So essentially, what this last part is asking you is come up with some sort of series that converges to pi on 4, some sort of series of constants. If we plug in a suitable value for x into our Fourier series, what we would like to do is get a simplification, and in particular, a series of constants that we can use. Now, let's consider the choice, say, pi on 2, x equals pi on 2. Now, think about sine, the values of sine of odd values of pi on 2. Okay, so think of sine pi, sine 3 pi, sine 5 pi, sine 7 pi. Well, it's either positive 1 or negative 1. And in fact, it oscillates between the two values. So I'm going to use that choice here, the x equals pi on 2. Sometimes there are other simpler choices, but that one is enough for this particular question. So let me show you. Okay, so if I go up here and I plug in x equals pi, I'll get some series of constants. Okay, so you can simplify in the following way. Okay, so if you want to just check it, think about the first, think about k equals 1. When k equals 1, this is just sine of pi on 2, which is positive 1. When k equals 1, minus 1 to the 0, that's positive 1. Then it'll go negative 1, then positive 1, then negative 1, then positive 1. Okay? Now also, note that at x equals pi on 2, g is continuous, and its value is 1. So by Fourier's theorem, this must equal this must equal 1. So now I've got some sort of series in here that I can rearrange. I can take the pi on 4 to the other side. And I get a special series known as Gregory's series, or it depends on what part of the world you come from. But just to write out a few terms of this series, we're going to get something like the following. Okay, so there is our series representation for pi on 4.